Okay, there are some homework problems with the exercise sheet outside.
They're actually inside.
They won't be necessary to
tested.
follow the lecture, but they will definitely be useful to continue following it. Let me start with the definition. Of matrix rigidity. It was defined by Valiant. Let's start with the matrix. For simplicity, I'm going to take square matrices and Valiant matrices. And we want to reduce the rank of A to some value, some target value R. Okay, so that minimum number of changes is called the rigidity of the matrix A for target rank R, and we use this notation for that. It's the minimum number, so this notation again is the number of non-zero entries in a matrix. For all such matrices C, which we call the change matrix, so that when you add the change matrix, the rank becomes at most R. Okay? So the least number of changes that you can make to the entries of A so that its rank becomes at most R. Okay, so that's rigidity. What's an easy upper bound on this number? That's essentially a trivial exercise, and it's the first exercise in the problem sheet. So for all A, and all E are n by n matrices for us, you can show you only need to change, you take some R by R minor, and then change everything in the complementary minor, and you can make sure that the rank is at most R. So that's an easy upper bound. You know, what about lower bounds? Okay. So Valiant himself proved, and this proof is, actually we'll come back to this, if the field is infinite, then a generic A will have as much as n minus R squared rigidity. We'll actually review this, and for finite fields, again this is an exercise, and you can show for most A, it's some constant times, apart from a log factor, this is optimal. So for almost all matrices, we actually know that the rigidity is about n minus R quantity squared. So what's the challenge here? What's the main question about matrix rigidity? So the main question is to find explicit matrices A so, I mean, when I say explicit matrix, I really mean here an infinite family of matrices, and here I mean A sub n, and epsilon and delta are some constants. I will not formally define what explicit is, but the nicest definition would be A should be polynomial time computable in some reasonable model of computation. Again, I will not spend too much time there. But we will see examples where we would consider matrices to be explicit and examples where we don't consider them to be explicit enough for the purposes of complexity. So why do we want to answer a question like this? I mean, in some sense, we know the exact answer essentially for almost all matrices. So the motivation for posing this question by Valiant comes from arithmetic complexity. So let me do that here. So the goal is to prove lower bounds on arithmetic complexity, and I'll define the model in just a second, of computing the linear transformation given by the matrix A. And the model is very simple. The only operation that we do is compute linear combinations. So if you say U1 and U2 are some linear combinations of inputs that you've already computed, in one step you can compute, let's say these are scalars alpha 1, alpha 2, you can compute V, which is a linear combination of these two things. This is the only operation that we do. So in order to compute this linear transformation given by A, you start with your input vector x1 to xn, then take linear combinations of a bunch of those, and take linear combinations of those guys, and so on. Okay, and eventually you will get your y's. So let's say this is y. Okay, so that's a circuit. The input at the bottom and the computation flows upwards, and the size of this circuit is the number of edges in this graph, or the number of wires. If you think of these as wires, this is a plus. Okay, and scalar multiplications are free. These are scalar multiplications, and we are only counting the linear combinations that are done. And the depth of the circuit is the length of the longest input to output path. So it's the longest chain of dependencies in this computation. So that's it. Okay. So questions? All right. So now it's easy to see that for all n by n a, you can compute this in depth order log n and size order n squared. Okay. And a big complexity question, is this still into that? The big complexity question is find interesting linear transformations A that require logarithmic depth and superlinear size simultaneously, or rather superlinear size. Actually, let me rephrase this so that it's less ambiguous. That cannot be computed by depth log n, so we don't sacrifice depth, but size we want to be linear. So small circuits of logarithmic depth, and you want to show that such circuits cannot compute some explicit linear transformation. So that's the lower bound question that we would like to solve. Linear transformations obviously are extremely important. They come up all the time in computations. One of the interesting linear transformations, of course, is the fast Fourier transform, where you actually don't require size order n squared, but order n log n. But is that optimal? So that's one of the fundamental questions, right? So Fourier transform can be computed using n log n size and logarithmic depth. And we would like to know whether it's conceivable to have a linear time computation for the Fourier transform. And if you want to disprove that, if you want to prove that it cannot be done so efficiently, one way to solve that is to address the rigidity problem. So the theorem that Valiant proved, and that's the motivation here, is that if you show that the rigidity of a matrix is large enough for target rank constant fraction of n, then this linear transformation cannot be computed in log depth and linear size. Okay?
So it's kind of a theorem reduction to depth 2 circuit. Right?
Sorry, yeah, the proof?
Sort of reduction to depth 2, the theorem.
In some sense, yes. I mean, actually, I wasn't going to prove the theorem, but intuitively, the proof is some kind of a depth reduction. Now that depth reduction has become such a major theme in complexity, we can think about the proof. Valiant proof also is a kind of depth reduction. Basically, a graph theoretic argument that he uses from a previous result is if this graph, this linear circuit, is size order n, then you can identify a small number of vertices, which if you pull them apart from the graph, meaning that you take those vertices and all the adjacent edges, then the graph shrinks, in the sense that every input to output path that avoids those vertices is actually short. Okay? So that's kind of a depth reduction. But the number of nodes that you need to remove to shrink the depth is actually quite small, and that gives us the rank bound here. Okay? So by removing a small number of vertices, and therefore you sort of route your computation through those vertices, and the rest of the computation flows through very short paths. And if it is a short path, you can just expand it into a tree, and that's the depth 2 circuit that you're talking about. And that depth 2 circuit, because it's short, meaning the depth is now instead of order log n, it is some delta log n, or some small enough delta, and that's how you get n to the 1 plus delta. Okay? A depth 2 circuit of size n to the 1 plus delta, and that's sort of the rigidity. Those are the changes that you're making. The depth 2 circuit is the changes. Okay? So it's very fast. I don't want to get into the details, but basically the idea of the proof is to reduce the depth of the circuit by removing a small number of vertices and use those small number of vertices and the residual circuit to get a low rank approximation of the original matrix. So that's the intuition. All right? Okay, so from now onwards, let's just focus on this question. Just focus on proving lower bounds on rigidity of matrices. So what would be a good candidate for proving a lower bound? We'll use the definition here. Maybe I will use this. Okay, now I'll just write here. Find A. So that's our central question. And we'd like to get as close to answering that as possible. So what would be a good candidate matrix for which you hope to prove that changing its rank to R, let's consider a generic or general R, although eventually we are interested in this value of R, so that you will require a lot of changes to bring the rank down to that value. Any guesses? Pick your favorite matrix. Almost every matrix is
Tandem
rigid.
on.
Sorry?
Tandem on.
Excellent. Okay, so there are a whole bunch of van der Waals matrices depending on how you. So I'll write this. I don't know. I'm used to writing this with the x's denoting the rows. I know a lot of people are used to writing them as columns. That's why I'm writing this explicitly. All right, now, what do we want these xi's to be if the matrix wants to be explicit, if you want this matrix to be explicit, okay? So, one interesting choice for xi is xi being all positive reals. Why am I choosing that? The reason I'm choosing that is if you choose, of course, if xi are generic, everything I'm going to say is true, but let's choose xi to be positive real so that I can actually put numbers here. Actual numbers there. All right? So if I do that, then the interesting property is that such a van der Waals matrix has all minors non-zero. Every subdeterminant of every size of this matrix is non-zero. So it kind of looks very robust, because if you want to reduce the rank to, say, R, you pretty much have to kill every R plus 1 by R plus 1 subdeterminant. And you have to do this for every value larger than R. I mean, of course, yeah, if you do that for R plus 1, then you have done it for everything. But anyway, so in some sense, a matrix that has, so these are called totally regular, this is a class totally regular matrices. So these are matrices for which all submatrices, square submatrices, obviously, all square submatrices are non-singular. So this looks like as robust as you can get, all right? So what can we say about matrices that are totally regular? So now I want to prove the theorem. It's actually, let me not state the theorem yet. It's actually easy to arrive at the theorem by just looking at this problem. So if I have this matrix where every R plus 1 by if I want to hit every R plus 1 by R plus 1 submatrix, I need to choose enough. So the question then is this, and that's how many changes do I need? Just combinatorial argument, I'm not doing any algebra or linear algebra here. How many changes do we need to hit every R plus 1 by R plus 1 submatrix? Right? That's the question. So that clearly gives us a lower bound on rigidity. Correct?
If you keep just diagonal, you will not keep all.
No, I mean, if R is small enough, then many submatrices. Let's say R is n over 100, then many little matrices.
But just keeping diagonal.
Yeah, but I mean, there will be many small square submatrices all over the place. Right?
And These are combinatorial submatrices.
Right, yeah. I mean, yeah, these are just, I mean, when I say R plus 1 by R plus 1 submatrix, I'm picking some I1 through I, or J1 through JR, and some I1 through
J1 through JR plus 1.
R plus 1, sorry, yeah, R plus 1, and I'm looking at the intersections of those rows and columns. It's, yeah, just submatrices. All right? So the way we're going to answer this is to actually use, it's a combinatorial problem, so we are going to think about A, the entries of A are, as a bipartite graph, or rather the coordinates of A. So we are going to look at a bipartite graph with vertices 1 through n, 1 through n, and you put an edge between I and j if that's an unchanged entry. So if you changed S entries, this graph, let me call this G, G has n squared S edges. And now we are asking how many edges, and what is a square submatrix? A squared submatrix corresponds to a bunch of, R plus 1 vertices here and R plus 1 vertices here. And if it is not changed, this will be a complete bipartite subgraph, right? No changes in that. Mine R plus 1 by R plus 1 submatrix means you have a complete bipartite graph. So let me use a symbol here. Let's call this M. So how large or how many edges do we need, or rather the other way around? Sorry. So what's the maximum number of edges in G to avoid an R plus 1 by R plus 1 complete bipartite graph? Right? So this is a well-studied question. It's called CERN problem. Well, in general, not just UV complete bipartite graph. And there is an upper bound known on the number of edges that a graph can have while avoiding such complete bipartite graphs. So the maximum number of edges in a bipartite graph when you forbid an R by R, or R plus 1 by R plus 1 complete bipartite graph. And that's a known quantity. And so this is at most, right, n squared minus this, is this number. And that number has a formula. But there's an expression of amount that we don't have to worry too much about, but I'll write it down. We're talking about an R plus 1 by R plus 1, so it will be something like R to the 1 over R plus 1. This is actually not so critical for the computations, but I'll write it n minus R. This is critical, times n to the 1 minus. So roughly speaking, it's n. So you have n squared, right? Potential edges. So if you sort of think about this as not too big compared to a fraction of n, so this is like something like n to the 2, right? N to the 2 minus 1 over R plus 1. That 1 over R plus 1 is the loss, in the exponent. That's it. And then there is some. Okay.
So what does that say? R to the what?
R to the 1 over R plus 1. So it's really a small quantity. You don't have to worry about that. So if you just use this bound, bound, you will conclude that S is at least, well, I mean, you have to put some restrictions on R so that these calculations make sense. But I'll just omit all of those and say
Well, if we,
something like this. Sorry?
I mean, we're interested when R is equal to epsilon times n.
Right, yeah, that will be fine, yeah. Well, that will be fine in the sense that will not violate these calculations, but it will be uninteresting. Sorry, R log squared. Some large enough R, but not too large. Essentially, you get omega n squared divided by R and the logarithmic factor. Okay, so let me see.
May I ask a question? So
Yeah,
maybe I
sure.
should pay attention.
Yeah.
So you go to some combinatorial problem. So
Right.
in the matrix, those entries that are changed correspond to a bipartite graph. Unchanged.
Unchanged entries. Yeah, unchanged entries.
So, okay, and now what is the
So you want to.
this rank condition? How does it translate complete bipartite graph? What do we do exactly?
Oh, you want to hit every R plus 1 by R plus 1 submatrix. Or in other words,
Okay, so
you
now that's already a different question because hitting is not.
oh yeah, that's not
Okay, so
that's not sufficient. That's necessary. Yes.
Okay,
Of
so
course,
we can
yes,
get
yeah.
this. This is
Yeah,
hitting. I see. So this is like the combinatorial problem that you are now studying. It's not
Exactly.
the original.
It's what? I'm sorry. It's not.
It's not the original question of rigidity.
No. I mean, it's not. I mean,
Okay.
otherwise we would have
Sorry.
gotten a
I
better
didn't
one. But
understand.
yes, it's not. Unfortunately,
Okay.
yes. Yeah. So So exactly. So all I'm doing in this board is try to estimate a lower bound on the number of entries that you need to change in order to have at least one change in every R plus 1 by R plus 1 submatrix. That's it.
Okay.
With a certain probability, or
I'm sorry?
with a certain probability?
No. Absolutely no probabilities. Yeah.
I just think I'm missing something. So I have a bipartite graph, right?
Right.
And I want to figure out the maximum number of edges in that graph that I can remove and still leave R plus 1 by R plus 1 complete bipartite graph.
Not leave, actually.
Leave?
No, not leave.
Oh,
You
okay.
you want to not have any R plus 1 by R plus 1 bipartite graph.
I see.
That's forbidden. R plus 1 by R plus 1 is
Okay.
forbidden.
Thank
Yes.
you.
Yeah.
Okay, I understand.
I also have a question in relation to this graph, to
Yeah.
the problem. So is the left-hand side, is that like the column index and the other is the row index? Or
It doesn't
how is
matter,
it-
yeah.
How is that
Let's-
graph related to, is that the relation to the
You're
origin?
starting with the complete graph,
Right.
Sorry.
n complete bipartite graph, and you want
My
to
problem starts before, like how is that graph related to this question?
you want to touch each size R plus 1 minor. So you want to kill enough edges so that every R plus 1 minor is touched.
Okay, let's say the left-hand side vertices correspond to rows and the right-hand side vertices correspond to columns, right? And now, if there is no change in entry ij, you put an edge between vertex I and vertex j. Okay? So every non-change corresponds to an edge, and since we don't want to leave any R plus 1 by R plus 1 submatrix untouched, okay? You don't want any R plus 1 by R plus 1 complete bipartite graph in this graph, okay? But if you insist on that condition in a complete bipartite graph, it cannot have too many edges. And this number gives you the maximum number of edges that it can have. And therefore that number has to be at least the number of non-changes you have. Yes?
N square over R seems trivial, yes? So the gain here is like logarithmic.
N squared over R for these matrices,
Yes.
if you use a probabilistic argument, yes, yeah.
I think I have like a two-line easier.
for some specific matrices, but for arbitrary, totally regular matrices n squared over r, probably okay. You can just divide it
So
into
there can be at
Omega
most
is-
r columns that choose
Yes.
n minus r over r rows.
yes, yeah. Actually, you're right. I mean, n squared over r. In fact, one of the homework problems is that n squared over r is actually very easy to prove for most matrices. But this is the best known, so I want to, yeah. And in some sense, these are the matrices for which you expect almost maximal rigidity. Right? And so this is. So the,
So,
yeah.
is it known that a random Vandermonde matrix has high rigidity, a generic Vandermonde matrix?
No, in fact, yeah, that was going to be the open question that I was I'm going to mention at the end. Yes, yeah, no, it's not known. So, okay, what's the conclusion here? So, the conclusion is for these matrices, the rigidity is omega n squared over r log n over r, essentially. So you kind of put conditions in R. So for a reasonable range of target rank R, you get that bound. So that bound is far from what we want, but unfortunately, that's the best we know so far for explicit matrices. And there are many such matrices. So here is one example, and there are a couple more examples in the homework. For example, the Cauchy matrix, whose entries Cauchy matrix xi plus yj.
Why do you require r to be less than n over 2?
Oh, I'm just approximating, rather estimating n times n over r. I have something like n times n over r, and I'm going to say that's n squared over some 2. That's all.
Yeah, but if r is epsilon times n for any epsilon less than 1, don't you get the same?
Yeah, sure. I mean, I could put here 1 minus epsilon. Yeah. Constant change, that's all. Okay. And the most interesting matrices, from the point of view of explicitness and also from the point of view of applications, are matrices over finite fields and derived from error correcting codes. And I will, again, I will not spend time on that. One of the homework problems is that. So, because this is the best result known so far on finite fields, let me just state that. So, now consider a finite field of Q, and the generator matrix of an error correcting code is a K by N matrix. In coding theory, they write vectors as row vectors, so we'll stick to that notation. So the code given by G is U transpose G, so the row space of this. So this is clearly a subspace. Okay, and the distance, the minimum distance of the code is the minimum weight of a code word. 0 C. Okay, so what this means is that in this subspace, if you take any two vectors, C1 and C2, they differ in at least this many. So let's call this D, this many coordinates. That's a correcting code. Okay, maybe many people know this already. So, so such a code is called NKD. So this is D. NKD code. And using algebraic geometry codes, achieve codes of the kind n over 2 is a highly non-trivial result. Codes, okay? And now by converting G into standard form, I can write G as identity followed by matrix A. And if such a matrix G has good distance, such as this, then you can prove that the matrix A has almost the kind of property that we have for totally regular matrices. In other words,
Sorry, what is
Yes.
n, k, and d again? I'm confused.
K is this dimension.
No, but in,
Yeah. K is the message length, N is the code word length, D is the minimum distance. So A has the property that every 2t by 2t submatrix has rank at least t for t greater than this, let's say, maybe d plus 1. Okay, so
A now?
this matrix.
Oh,
I want a square matrix. That's all.
okay.
So error correcting codes, good error correcting codes, give you good matrices. These sort of totally regular kind of matrices. Not exactly because the rank is not full, but constant fraction of the full. But that's still okay. The same arguments will work, and you can prove that. And therefore, the conclusion is that there are explicit matrices, namely matrices coming from these kinds of error correcting codes, for which we can prove a rigidity lower bound of this and square over times log n over r. Yes.
So, in particular, a generic matrix is totally regular.
Yes.
So
Yeah.
how is it that the bound gets, how can you possibly get a better bound?
We don't.
Or-
It's much worse.
Okay.
It's
Why?
much worse because there's an r in the
set
denominator.
r equal to epsilon n,
Yeah.
you,
Yeah, if r is epsilon n, this is trivial. I mean, this is linear.
doesn't say a whole lot about the.
That's the interesting values of target rank that we want to consider. Sorry.
I was wondering about the definition of distance. Is that can you explain that?
Yeah. So formally, it's the minimum number of the minimum weight of a vector in the row space, non-zero vector in this row space, the weight being the number of non-zero coordinates. Okay, but that's also equal, because this is a vector space, to the distance, meaning the number of coordinates in which they differ, between any pair of vectors in this space. And that's why it's called the minimum distance. If you take any two vectors in this subspace, they differ in at least d many coordinates. All right. So
Maybe another question. What
Yes.
is this Cauchy matrix? When is it totally regular? So what assumptions do we need on it?
oh yeah. I mean there are some standard assumptions. Xi and Yj should be distinct, and Xi plus Yj should not be 0 for any. Other than that, you don't need anything.
That's all.
That's all. All right. So, over finite fields, that's unfortunately the end of the story. We don't know anything better than that, and that's kind of, those are very nice matrices, but the bound is quite uninteresting. Okay, all right, so now what do we do? I mean, where are we failing, right? So one thing that is relatively easy to check and well known is that you cannot improve this number just by combinatorial arguments. So if you want to hit every r plus 1 by r plus 1 submatrix, the bound that I wrote down is optimal. Okay? But actually there is an even worse conclusion, which is a result due to Valiant himself. So there exist totally regular matrices A. Such that AX can be computed in log depth and linear size, which is in some sense bad news if you want to prove lower bounds, but good news when you want to compute linear transformations. In particular, this means that the rigidity of those matrices is small. So total regularity, this condition which we thought is quite natural and nice to prove rigidity lower bounds, actually turns out to be too weak to prove the kinds of lower bounds that we need for Valiant's criterion. I will not prove this theorem, but again it follows from a graph theoretic construction, follows from superconcentrators, which are some interesting graphs constructed from expander graphs. Again, I won't go into that. Superconcentrators of linear size and logarithmic depth. Or actually, I should say, the construction also. From here to computing this is actually a result due to Strassen. Okay, so this condition of a matrix being totally regular is actually not good enough, and I don't know any other property that that we could sort of use for a whole class of matrices to give explicit matrices like this, like code matrix or any of these matrices on rigidity. So what I'm going to do now is to consider results where we don't get lower bounds for explicit matrices. We get stronger bounds, but we sacrifice on explicitness, and we use more algebra than what we have, or rather, we haven't done anything in algebra so far. So then simple combinatorial arguments. So it's almost time for the break. So let's take a break, and then when we come back after a short break, we'll look at some algebraic arguments for rigidity.
Okay, we will reconvene in 3 minutes.
Such matrices. So xi are now generic. So we are now switching to complex numbers. Yeah, I mean, of course, you would expect such matrices to have highest possible, or at least almost as high rigidity as highest possible, but we don't know how to prove. So that's actually one of the big open questions, and let me state it right away. That's a generic So yeah, unfortunately, even such a basic question, we don't know the answer. So what I will do now is prove a much weaker theorem. And you will realize that the proof is actually quite simple, and it's not. Oh, okay, let me just say square over 4 for small enough epsilon. Okay? So,
Epsilon is
yes.
constant, picked once and for all?
The epsilon?
Yeah.
Yeah.
Okay. Just smaller of this.
Yeah, small enough constant epsilon.
Yes. Sentence small enough sounds like it's true.
Yeah. All right. Okay, so at least asymptotically, for small enough rank, we know that it has a quadratic rigidity. And the way we prove this is to, I will sketch the proof because I'm probably going to run out of time to do everything I want to do, is a notion that Shoup and Smolensky have defined in the context of proving circuit lower bounds, but that turns out to be useful also to derive rigidity lower bounds, at least in some limited sense. And this definition, for this definition, we will just think about sequences of numbers, complex numbers, and I'm running out of symbols, so let me just, actually let me misuse notation and just say A. So you're given a sequence of complex numbers, m complex numbers, and in our case, A will be a matrix, and we just write the entries of the matrix in some order. Okay, so that's why it's okay to do this. And now what we are going to do is consider take some distinct t elements of the sequence, multiply them, that's a complex number, think of that as a vector over the rationals, and then look at the span. Okay? So let's put a symbol there. So it's some d, a, t is the dimension over the rationals. J, equals 1 to t, I want to write it distinct. J is okay. So it's just the number field, dimension of the number field generated by these t tuples. Okay? Now, why is this interesting? So one little lemma that you can easily prove is if A, let's say, so now I'm thinking of it as a complex matrix, if has rank R, then this quantity, it's very easy to prove, is at most when R, sorry, this is not, this is T, R is the rank square. Well, the proof is actually, it's easy to see. Let me just, so since A is of rank R, you can write that as an n by R and an R by N matrix, and therefore essentially these Aij's are inner products between rows here and columns here, which are, there are only NR such variables here and NR such variables here, and so if you write these tuples in terms of as linear combinations of tuples from this matrix and this matrix, you will get that they're at most pattern. It's a very simple counting argument. So that's it. So if low rank matrices have a small Shoup-Smolensky dimension, that's the main point. And now it's very easy to prove this. So how do we prove this? Suppose C is the change matrix. Then, yeah, yes.
So you define this dimension for a vector. A is A1 up to AN, or
Yeah.
now you have a matrix.
The
Well,
A's
so
are the
I'm-
Xij's.
Yeah, so these are just the entries of the matrix written in some order.
M equals N squared.
Yeah, this M
Ah.
is my,
Okay.
this N squared.
Okay.
Yeah.
Good. So I think of it as a vector.
Yeah.
Good.
Size of C is the rigidity. And so we know two things. Well, actually we know at least one thing, that the dimension, this Shoup-Smolensky dimension of V minus C, so rank of V minus C or V plus C is at most up. So this guy we know is at most NR plus P squared. Okay. Now we want to prove a lower bound on this using the genericity of the van der Waals matrix. Okay. So now in this matrix we made a bunch of changes. Actually, let me call this S so that I don't have to write the whole thing. S. And so change matrix that achieves this, and S is the rigidity. Okay. So there are S changes that I made into this matrix, and therefore by a simple averaging argument, N over 2 rows have at most 2. So the average number of changes per row is S over N. S is the total number of changes, the average number is S over N. So if you take twice the average, you have at least number 2. Okay.
How about those two S over 1 changes?
Sorry?
No, good.
Yeah. All right. So now I'll just ignore the elements that have been changed. Now I still have N minus 2S over N powers elements are unchanged in these rows, each of these rows. Right? And so if I just take one from each of those N over 2 rows, one of the powers of Xi's, right? They will all be linearly independent over Q. Okay. So what we know is, I'll write N over 2 now, is at least that many. You take any one of the unchanged entries in one row and any one of the unchanged entries in the next row and so on, and you can do this up to N over 2, and all these monomials are going to be linearly independent. That's it. So you just compare, so here you put t equals n over 2, so d v minus c n over 2 is at most. If I put that nr plus n over 2 squared, and if you just compare, you get s is at least n minus nc r squared divided by 2. Okay. So this c is some constant based on how you approximate this, and this n over 2 is anyway. So basically, it is n times n minus constant times r squared, and that squared is what's killing us. Rather, I mean, that square sort of comes from this, and I don't see how to get rid of it. Anyway, so that's kind of all we know about generic van der Waals matrices. Actually, we know a little more, but I'll come back to that.
Do we know about some explicit small dimensional other varieties for which we can prove that it has high rigidity rank?
Yeah, we, not varieties, but we do know some special, in fact, I'm going to write one next. So using the same, essentially the same ideas, because the problem here is that you need to, because in each row you have powers of the same variable, you cannot take, cannot mix elements from the same row. So you can generalize this argument, and I will not prove it. The proof idea is very similar to this, but you will do better than this because you have more freedom in choosing these tuples, and that theorem is this. So let P be this matrix square root of Pij. Pij are distinct primes. Then you can show that something like this. So this definitely meets Valiant's criterion of P of something like this. Okay. A very similar argument. Now, earlier I could not take t to be larger than n because of this, because I need to pick one element from each row. But now this matrix is sort of very random looking, and there is no, you're just throwing a lot of quadratic irrational numbers into the matrix, and that's really all you're doing. And the same argument allows you now to choose larger t, and if you choose larger t and using similar computations, you can get better lower bound on the rigidity, and you actually get a quadratic lower bound for R epsilon n.
Does it imply quadratic lower bounds for complexity or not?
It does. Not quadratic, superlinear. Yeah. Actually, it does also imply nearly quadratic. You can actually derive n squared over log n lower bounds for this matrix, but not through rigidity criteria. So there is another path to proving lower bounds on linear circuits, not going through rigidity, but directly applying these kinds of dimension arguments to the circuits, and then you get n squared over log n. But yeah, so you do get circuit lower bounds, but you also get quadratic lower bounds on the rigidity. Yes?
What if you don't take square root? What if you just put the prime? Is it?
Well, at least in that case, this proof doesn't work.
Sorry?
This proof definitely doesn't work, but I don't know if if there is a way to prove.
I see.
Yeah.
What's who proved this theorem? What is the theorem?
Sorry.
What theorem? Like who proved this theorem?
Oh, it's me. So I mean, you can play with this a little more and get interesting or slightly stronger lower bounds. But let me stop here and move to algebraic geometry, where you can do even better. But then every time you do a better lower bound, you get a better lower bound with rigidity. About rigidity, you lose something. Like here, I mean, you lost the explicitness because these are not rational numbers, and these are you really need them to be rational numbers for the whole proof to work. And this is why it is not as satisfactory as we would like. I mean, as interesting as we would like from a circuit complexity point of view.
Can you run the irrationals and show that maybe you truncate at some point?
Yeah, I mean, yeah. So if you can prove that if you truncate, something continues to hold, I don't know what that something is, and rigidity can be proved, that would be fantastic. But I don't know how to do that. I mean, I don't know how to get some kind of a rational approximation to this proof, or the arguments in this proof. Yeah, it will be very interesting. Yeah, I mean, ideally we would like rational approximations up to polynomial precision, but forget polynomial precision. Any finite precision rational approximations to these matrices can we prove that they are rigid. I mean, we believe they are, but I don't know how to prove it. I don't know a technique, an approach how one can prove that. All right, so now since I'm going to run out of time, actually I should have left here. Anyway, so let me now look at rigidity from an algebraic geometry perspective, and what I'm going to say will be very elementary, and there are better experts in the audience on algebraic geometry than me, and there are actually much stronger results than what I'm going to say that have been proved. So I will just give a brief introduction. So, all right, so now let's we know very little, so this is more like an open direction than explaining what we know. Okay, first of all, the easier thing to look at is the variety of matrices. Actually, let me just make and then matrix of indeterminates. Sorry, actually no, I'm jumping ahead. Not yet. Sorry. Okay. That's a well-studied, or depending on who you talk to, studied object. And it's really the variety defined by the ideal I and R, where I and R is the R plus 1 by R plus 1 minors of an n by n matrix. Okay, so we know about how to define low rank matrices in algebraic geometry language. Now let's try to do this for rigidity, and that's not hard to do. So let's use rig n or S to be the matrices A, complex matrices, such that the rigidity of A for target rank R is at most S. Okay. So when he's a matrix in this set, he's in this set if A can be written, so if you take A, so there exists a change matrix C such that rank of A minus C is at most of or A plus, doesn't matter, okay? So that's when you put it here. And what is C? C is, C has at most S non-zero entries. So this also we know. Let me write that as L because it's a linear space. L and pi to be the set of all matrices C such that non-zero entries, support non-zero entries of C are indexed by C by pi, where pi is a subset of it's a set of coordinates, set of entries, and well, okay, so that's it. Okay, so A is in this set if and only there exists a C Okay, so it's easy to understand matrices of small rigidity in terms of these two varieties. And for, so let me, okay, so let me, just for notational convenience, let me, in fact, it's actually useful for pi, pi, where well, the notation should be obvious. I'll just say pi here. Okay. All right. So by making changes in the pattern pi, you're able to reduce the rank to R. Okay. So now this is easy to understand. What is it? You took the matrix A, and if you think about this, an entry here is rather the variety rather, I'm sorry. How am I going to say this? Okay. Okay. You took a matrix here, and when you subtract a matrix from here, you got into a rank. So if you consider a matrix X, and R, and if you consider a set of extra variables indexed by pi, so the minors R plus 1 by R plus 1 minors of X plus T pi are 0.
No, I think you mixed notation there.
There do I? Okay.
Yeah, you
I'm
want
using integers.
A plus T pi.
Right.
And
A plus C really, okay, yeah. Yeah.
Yeah, A plus T pi is equal to X.
Yeah.
No.
Sorry? A plus?
You're mixing notation.
Yeah, I am.
Because the minors of R plus 1 minors of A are
Yeah.
0, not A plus T pi.
No, not A plus C, actually. A is not.
Yeah, A is not in there.
Yeah,
Right.
A plus C. Okay.
Yeah.
So, okay, so since I'm actually running out of time and I'm trying to compress, let me just say this. So, the way to think about the Zariski closure of this guy, okay, so this is what we want to understand, right, is you take the ideal and then you eliminate. So this ideal is on all n squared variables. What I was trying to say is eliminate variables indexed by pi out of this, and then you get an elimination ideal. And the variables here are variables that are outside this pattern. And the main claim is that it's actually, it's not even a lemma, but anyway, So read n r pi, the closure of that, is the variety defined by this elimination ideal. And intuitively, this should be very clear. Okay. So what we are doing is, when you take a matrix in the variety defined, or the Zariski closure of this, the difference between that and the rank R matrix is exactly the matrix whose support is pi. Okay. And if you eliminate the variables in pi, pi is the one that, the matrix C is the one that's existentially quantified. So in some sense, in order to understand the matrices for which there exists a C satisfying this property, you would like to eliminate the variables corresponding to C and get an algebraic condition on the entries of it. And that's exactly what we are doing. Okay. So for every pattern pi, if you eliminate the corresponding variables, you get a whole bunch of elimination ideals for different patterns, and the varieties corresponding to these different patterns, the elimination ideals of these different patterns are exactly the Zariski closures of these rigidity varieties. Okay? And in fact, they are the reducible components of the rigidity varieties of the Zariski closure of this. Okay? So that's kind of the geometric picture. Now, what do we do with this? So one thing that we can trivially do is try to understand what kinds of polynomials live in this. Because if you remember the previous argument, if you know something about the degree of polynomials on which a matrix should vanish if it has small rigidity, then you could construct matrices which don't satisfy such a polynomial equation. Okay, so one approach would be to try to get degree upper bounds on polynomials in the elimination ideals of these low rank matrices. Yes.
Is there anything known about how the pattern corresponds to what the dimension of the image is? Like if you change the pattern around, how does the dimension of this projection?
As long as the size of the pattern is the same, it would be the same.
No.
No?
It depends on how pi.
The
Pi is there's a kind of generic
correct. Okay.
dimension, but if you have, say, more than n-1 changes in a row, if you have n-1 changes in a row, then the dimension drops, for example.
N minus R. N minus
N
R.
minus R. Yeah, so,
Right.
but for for quote most, there is a basic dimension and then it can drop.
Actually, yeah. Right. Yeah, but I don't know if there is a systematic way to explain that drop.
Yeah, there's a theorem called Terracini's lemma
Right. Yeah.
that enables you to calculate this via infinitesimally, and you just look at the intersections of the determinant spaces, and if they're non-generic, then the dimension will drop.
Right. Okay. Yes. Yeah, remember that. Okay. So one thing that's well known already is some very exponentially large upper bounds. Right. Okay. So the effective inertial length shows that I will not state the theorem. There are several results. Polar lines, Schnorr, with various conditions, and there is paper that we use, Wittgenstein and four other authors. So there are several results, but instead of stating the theorem, let me just say what it implies for us. All it implies is that there exists a polynomial g in the elimination ideal degree of g is at most very bad, n to the 2n squared or 4n squared. So let me put a constant, some small constant c. Okay. So once you have such a degree bound, then you can construct matrices which don't satisfy polynomials of that degree. And so if you construct a matrix A which has roots of unity, J, okay, let me use something else, JK. PJK are primes. So this is a primitive PJK root of unity. PJK are primes that are all bigger than that number. Then this matrix, so you have to use a bunch of parameters here, which I didn't specify, but the main thing that you need to argue here is that the size of pi is, the pattern is at most n minus, actually let me just write exactly, into n minus large squared minus 1. So 1 less than the maximal rigidity. So if you consider the rigidity varieties for 1 less than maximal rigidity, then the elimination ideals will have polynomials of degree at most that, and then you can construct matrices that don't satisfy such polynomials, and that will give us a theorem that this gives you some sort of a finite bound on the algebraic degree of elements in the matrix A, but it's still uninteresting for the same reasons, and in fact even worse than the previous matrices because of this high degree. So since I'm almost out of time, actually I wanted to say something about the more recent paper that uses much more sophisticated algebraic geometry, but all 4 authors are here, and we can get a lot more accurate and a lot more intuitive description. Let me know if I'm spelling your names right. I better look at them before someone gets offended.
I don't get offended, it's okay.
Sorry.
Since the authors are here, you don't need to spell their names.
Yeah, okay, all right. Now these names I know how to spell. Okay, so they actually take a deeper look at the algebraic geometry of the rigidity varieties, and like JM was saying, a much more refined view of these varieties, and several properties, general properties of the polynomials or generators of these ideals are given, and some of the conclusions, interesting concrete conclusions. I'll just say this is that Cauchy matrix and generic Vandermonde matrix. Well, these are all generic. and have maximal rigidity. There are many more results. I'm just stating these as concrete lower bounds on rigidity. Maximal rigidity for r equals 1. For r equals n minus 1, it's trivial. For but r equals n minus 2, it is not. So for a generic van der Waals matrix, we also know that for n minus 2, you have maximal rigidity. Okay, yeah, unfortunately, I can't say much more about it, partly because I don't understand it, but partly because I'm running out of time. But let me state an open question, given all these crazy matrices that we have seen in the last few minutes, which seem to have very high rigidity, beating the bound that Valiant required for this criterion, but somehow we are saying they are uninteresting. And how do we formalize the uninterestingness of these matrices, and how do we sort of go, somewhere midway between uninteresting and interesting, right? So I already said something about generic van der Waals matrix. That's one of the open questions I was going to say. And another open question is construct matrices of rigidity, say n to the 1 plus delta for a target rank epsilon n in polydimensional number fields. So we are not asking for explicit in the sense of exact deterministic or polynomial time computability, but just put the entries of your matrix in a number field of polynomial dimension. So if this is exponential dimension, we know how to do it. If it's exponential in n squared, we know how to do it. So I don't even know how to do it in exponential in n. But polydimensional would be very interesting. Then in some rigorous sense, or I don't know, in a non-computational sense, these could be considered interesting matrices. Because then you have, in some sense, when do we want to think of a matrix being explicit? We want to have a polynomial sized representation of that matrix. Polynomial sized representation on a finite computer. And if the number field is of polynomial dimension, then you can represent it. The entries can be represented polynomial size. So that's the reason why I think this would be interesting. So as a candidate for this, one of the matrices that I would like to think of is this, which is sort of, again, van der Waals matrix, but not very generic, not very explicit either, where these omega i's are pth through pith primitive roots of unity. Unity and pi are the first, or polynomial primes, okay, first 10 times, let's say. They should not be too big. So that's I think this is sort of, ideally what we would like to do really is if all these the Fourier transform matrix. The Fourier transform matrix, as I said, is one of the most interesting matrices for which you should try to prove rigidity lower bound, because that would imply that the Fourier transform cannot be computed in linear time. There you have just one root of unity, primitive root of unity, and the other omegas are just powers of it. So van der Waals matrix, but generated by powers of the same primitive root of unity. So now, I didn't write it, I erased it, but if you throw in large roots of unity all over the matrix, we know that it has large rigidity. And so this is sort of intermediate, and this also belongs to the class of van der Waals matrices, which we would like to prove rigidity for.
The degree of the field extension would be something like, would be exponential.
It will still be exponential. Yeah.
And log n or something.
Yeah. So that's why this is a question I would. I mean, this is sort of a candidate matrix, but any matrix which is in less than exponential n squared number field, I think would be progress. And polynomial dimension, I think, would be really, really interesting. I don't know if it has any implications to circuit complexity, but it's a clean mathematical question. All right, I will stop there.
We have some time reserved for discussion.
So what about tensor rigidity?
Oh, good question. So actually, tensor rigidity was defined and studied, but I know only one paper doing that, and I don't quite remember the results. They are, of course, considerably weaker than what we know for rigidity, and they do have consequences to complexity, and that's the reason why they were defined. And at least in the context that they were defined, they wanted rigidity over G of 2, which is actually the most difficult field you would want to prove when you could think of for proving lower bounds on rigidity. So, over G of 2 we have no way to prove lower bounds. The finite fields that we were talking about, where we had even the n squared over log, n squared over r kind of lower bound, are for finite fields of some small constant, but not maybe 49 or something. Yes?
So how low would the degree of this G have to be to have consequences for complexity theory? Like if it was brought down to polynomial in n?
Yeah, so I mean, I think
Would
if you brought it down to polynomial in n, this question could be answered, but I don't know if it has any direct consequence, at least not to my knowledge, to circuit complexity. It may be possible. I haven't worked on deriving the consequence, but I have a feeling that it might be possible to derive consequences to circuit complexity. Yes.
Maybe it could be mentioned that these matrices you study, they look very similar to these well, people tried for many, many decades to prove lower bounds for the explicit polynomial, say just one variable.
Right.
There was this pioneering paper by Strauss in '73 where he came up with, he had a polynomial where the coefficients were just square root of the primes.
Yes,
These were roots of unity, and then, I think it's very similar also in terms of technique. Now this is the rigidity problem, it's related to
I think,
but I think the techniques are very similar, and so it seems that we get stuck always more or less at the same.
Right.
What was the variety in question in the Straussen problem?
The variety that this was just say this. Look at the set of polynomials in one variable that with multiplicative complexity of most r. It's not so. It doesn't have such a nice description as here.
I mean here the parametric description of the variety is very easy, and it's just a question of finding the equations, which is not so easy.
Right. In the other problem, the variety is much more complicated. Here, it looks so much simpler. Still. Okay. So maybe the problem is the elimination ideal. So if we could completely understand the elimination ideal.
Well, but you see, this is a very general theorem.
I know.
But this is a very special. The original ideal you're starting out with is very, very special, and one should use special techniques to get a sharper result.
The problem here, where we lose the information, is the elimination ideal. No.
Well,
so we don't know it exactly, so we just know there is some G of degree this and that. But if one would know it better,
it may be possible to understand the polynomials in this, the ideals of these varieties more directly, instead of trying to refine the process of elimination for these particular varieties. I guess that's kind of what you're saying. I think I think the geometric intuition for the rank varieties, and these are essentially the projections of the rank, the low rank matrices, varieties of low rank matrices, might actually give you, more direct information, and it may be possible. So I don't know. Well, I mean, again, these are determinantal ideals, and determinantal ideals have been very well studied. But I have, from my conversations with a few experts, it's not clear at all whether you can improve the bound, this degree bound, for determinantal ideals.
It's also worth mentioning that I don't know if it's co-authors, but at least one of the authors, Z. Rosen, also found very explicit equations in a completely different context for a completely different problem, but it solves this problem also. But again,
what do you mean
there's
by
still
this
no
problem?
consequences.
Polynomials here?
Yeah,
Yeah,
some
I see.
very interesting polynomials there, but just like what we did, there's no consequence yet, but he has found. I don't know who the other co-authors are.
Franz Kirai and Louis Stein.
Yeah, so.
Okay. Yeah, I mean, I think like they did for R equals, the polynomials that they have for these two ranks are very nice. I mean, once you see those polynomials, it's fairly easy to see that those polynomials are not going to be satisfied by generic 1-to-1 matrices, and they're fairly clean. And it would be nice to get such polynomials for larger ranks, or ranks away from small constant and away from n. I have no idea how to do that. Sorry, yes.
For understand this variety is reduced not only to fix some patterns
Yes.
but like if you want to prove something about rigidity, you need to prove it for all patterns.
Right. Yeah. So I mean,
There are many of them.
Yeah. Well, I mean, in every one of them, you have a polynomial like this, and no such degree polynomial is going to be satisfied by this matrix. Yeah. So you do have to look at all patterns. So I erased it, but the rigidity variety is the union of these varieties over all pi.
But it's kind of, even if you have all these polynomials, it would be not trivial to prove for some specific polynomial that it's has high rigidity.
Yeah, right now the only property of the polynomials we are using is their degree bound. So, I mean, since I have no idea how to write those polynomials down like they did for other values of the rank, we only use the degree bound. So it would be nice, definitely if you can get more structure out of these polynomials, then maybe you can construct nicer matrices. Yeah.
If you consider a random matrix with random plus minus one entries,
Yes.
is it known as
Yes. Yeah. So that's one of the homework problems. That's the last homework problem. Basically leads you to the proof. Over the real numbers, a random 0-1 matrix, plus minus 1 matrix, has rigidity omega n squared. Yeah. So that's why, constructing even 0-1 matrices of high rigidity is not hard if you are willing to settle for random matrices. So you really need some effective way to produce an infinite sequence of matrices, and that's why explicitness needs to be properly defined even for 0-1 matrices. It's like, expander graphs or error correcting codes, where again it's easy to produce random objects, nice objects, but much harder to produce explicit ones. Any more questions?
So would there be any, for this question, if you do it over the rationals or over 0-1 matrices, would that have any consequences?
Sorry, which question? This question?
Yeah. If you could produce matrices rather than
Well,
the number field would be over
Oh.
two, say.
Oh, I see.
Would that have any consequences?
I'm not sure. I don't know. Basically, I don't know how to interpret this polynomial dimension of a number field in a computational sense. I believe there is probably something that one can do, but I have not done that. Yeah, that's a good question actually. That's, yeah, I mean with some small rational, yeah, you don't want them, I mean, they can't be rational numbers, then the dimension would be not polynomial, it will be really small, but yeah, even then I don't know. I mean, even then I really don't know how to have a computational interpretation of that. But yeah, so in some sense this is a weakening of what you were asking, right? I mean, this is a much weaker question. I don't know what to answer. All right.
So we
Yeah,
send
sorry.
the speaker again.
Thank you.
And we reconvene.